Now let's go back to study the system response. Since you have already knew the concept of stability, from now on, we assume all linear time invariant systems we encountered are stable. We know if the system is stable for any bounded input, the output will be bounded. Here are some elementary signals. We have impulse signal. We know the transfer function is the Laplace transform of the unit impulse response. Then for step signal, the input is constant. Then for sinusoidal input, the input is sine or cosine functions. So in general, the output contains two parts. It has two components. One is forced response. This is because of the input signal. The other element, the other component is natural response. The natural response is also called impulse response. We know when the system is stable, the impulse response will decay to zero. The forced response, it is also called steady state response. Then the natural response, it is also called transient response. Then we know for general how to calculate the output for any given input signal if the transfer function of the system is known. The first step is to apply Laplace transform to the input signal. Then we use the Laplace transform of the input signal to multiply the transfer function. Then we get the Laplace transform of the output signal. Then we can use inverse Laplace transform to get the time function of the output. Now let's look at an example. We have the transfer function of the system. It is 1 over s plus 1. Here we have a single pole. It is at -1. Then we know the system is stable. Then we can discuss the response. For unstable system, it is meaningless to discuss the response, because eventually the response will be infinitely large. The input signal is a sine function with frequency 10. Now we want to determine the response to the input signal that applies at t is 0. The first step is to calculate the Laplace transform of the input signal. We can use the formula here. Then we know, since the frequency omega is 10, so the Laplace transform of the input signal will be 10 over I squared times 100 plus 100. Then we times the transfer function. We have the Laplace transform of the output signal. Then we can use partial fraction expansion to calculate the inverse Laplace transform. So it has two terms, s plus 1 c1 plus s squared plus 100 c2s plus c3. Then to know the value of c1, we can use cover-up method. To know c2 and c3, we can use the method of balancing the coefficient. Let me give you a few minutes to try to solve this problem by your own. Here is the partial fraction expansion. Then we can write the second term in this form. So here a is 0. So omega is 10. Since a is 0, we have 10 over 101 s. So omega is 10. So we write 10 over 101 by 1 over 101 times 10. So this will be omega. And here is B. A. Here capital A. For the first term, we can use this formula to calculate the time function. For the first term, it will be 10 over 101, so exponential minus 1t. Then we have a, so it's minus 10 over 101, so cosine 10t. We have b is minus, then another minus plus 1 over 101, then sine 10t. Then we can use this formula. So we have here small a, then this is b, then this term will be a squared 101 squared, then plus 1 over 101 squared, so it will be 101 squared over 101, be 1 over 101. Then we have the square root, then will be 1 over square root of 101. Then we have sine, so this would be the theta here, so sine 10t. Then we have the phi, so his arctangent, so this a over b will be minus 10, will be minus arctangent 10. When we see this time function, the output, so this component, it is the transient response. Here, it is the steady state response. So we see the transient response. The mode is determined by the transfer function. This figure is a plot of the time history of output. It shows the different components, y1 and y2, and the composite, y1 plus y2. That's the y. So here we have y1. It will decay to 0. So y1 is called the transient response. So y2 here, it is the steady state response. So the total output is the sum of the two. Here is the time history of y. So the input is sine 10t. So input You see in the steady state, if we only look at the steady state, when the time is very large, then we see the output, the steady state of the output. It has the same frequency with the input. That will be 10. Then the phase will be different. So based on the two plots, here we have the input is a ut, it is a sine function. Then the output, yt, we can also look at the steady state. It's y-axis steady state should be in this sine function. We see they have the same frequency. It should be 10, but the output, the phase of the output is lagged by arctangent. It's delayed by arctangent of 10. Then the amplitude is different. Then we can calculate the amplitude and the phase lag based on the transfer function. So we will discuss that later, but we can also calculate this amplitude and phase lag based on two plots. So for the input, the highest value is 1. So the output here is the highest value. So it will be this value, 1 over square root 101. Then for this phase, we can calculate the time, the highest value and the highest value, the time between them. Let's say the time is the t. We know the frequency. The frequency is 10 reading per second. Then we times this time, we multiply the time 30 unit is second. Then we get the reading, the angle, 10 times the t. That will be the arc tangent of 10.